All right. Okay. So let's continue. Last time we were talking about existence and uniqueness theorem. Existence basically tells you if you see a diffie Q, it's solvable. If it's not solvable, don't even bother. Second, we want uniqueness. That means if we have two solutions, they actually has to be the same. So passing one point with the initial value with the same diffie Q, you have to have the same solution. So that's what uniqueness tells you. The way to check it are pretty simple. You just want the derivative to be nice for that thing to exist. And you want the derivative to be nice. Meanwhile, the partial derivative with respect to the solution is nice. Then it's unique. Of course, all existence and uniqueness only works for a finite interval. Okay, surrounding your initial value. But the good thing is, once you know this one is unique and exists at one point from here to here, you can track this one all the way going to here and then set up another epsilon and track it to extend it, and then keep extending it until you cannot extend them anymore. So in general, you can extend the solution to as far as the situation allows you to. So it's not too bad. Okay, that's what we had last time. The third thing, we basically just want to talk about the application of uniqueness. What information can you gather from uniqueness? It seems like something really fundamental, yet useless. But now you can see several deep intuition you get from uniqueness. Okay, we will talk about several things. The first one is, last time we know we have a vector field, something like that. For different initial value, you can track a solution. Okay. Now you pick a different initial value, you're going to track another solution through the vector field. Okay, that's what we know. But now by uniqueness, you'll learn a very interesting fact. That is, if you have two solutions satisfying the same differential equation but different initial value, then clearly there are two different solutions, but they will never intersect each other, which means you could never have a situation in the vector field looking like this. That is guaranteed by uniqueness. Sounds good? Idea is quite simple. If they intersect, you start from here. Your solution is not unique anymore. So they never intersect. Okay, so this one implies different initial value of your system gave you different solution, which we mean never intersect. So they cannot just be partly different for an interval and then they become the same after a certain point. It's never happening. That's the first one. The second thing, which is interesting, that is, if you think about what we have for differential equation, usually what we have is we know the data for now, and once we solve it, we would like to predict what happened before and what happened after. So the uniqueness of solution basically makes sure that your experimental fact is reproducible. Okay, think about an easy example. You start to do a projectile by throwing a rock. Number one, this one satisfies a differential equation. What this one guarantee you is if you throw the rock with the same exact initial speed at the same exact angle, your trajectory will be exactly the same. Make sense here? You won't throw it with the same initial condition, and half the time the rock goes this way and half the time the rock goes this way. It's just not going to happen because your solution has to be unique. Therefore, if you have an experiment, you set up the initial condition. Say, hey, this is how I start my experiment. And then I let it go. You will always have the same answer. Otherwise, half the time you have a different answer. How are you supposed to write down the general law? Sounds good? So in real life, there are some differences in your experiment. That is because of noise, not because the original motion is not unique. It's just like every time you think the condition is exactly the same, but it's slightly different because of noise. Okay? But if they're exactly the same, you get the same solution. That's why you can reproduce your experiment no matter when you do it and how you do it. Number three, that thing gives us a very interesting concept, which is called the equilibrium solutions. These are some special solutions for your DFQ. And the way to find them is set f t y equals 0. What do you mean by that? Well, let's take an example. We have y prime equals y times 1 minus y. We know this is logistic growth. What is the initial equilibrium solution? That is going to be when y times 1 minus y equals 0. That gives you y equals 0 and y equals 1. Sounds good. What are they? Well, we have drawn the vector field before. I can't draw it by hand. We all know generally the solution looks like this. Now, if you pick a different initial condition, you got a different solution. Good so far? Cool. But there are two special solutions if you pick them. That is y equals 0 and y equals 1. If you pick your initial value to be 0, that means you have a logistic growth with 0 population to start with. Then your population stays 0. That's equilibrium 1. Similarly, if you start below the threshold, you grow to the threshold. You start above the threshold, you drop to the threshold. Still okay? But what if you start right at the threshold? If the environment is capable for 5,000 population and you start with 5,000 population, what's going to happen? Then your population stay unchanged because you're right at the threshold. That's the two special solution here. Sounds good? Okay. Now, go back and think about why do we set this one to be 0 again? You basically set y prime to be 0. What do you mean y prime equals 0? That means y does not change. So if you start from this point, then you're going to stay at this point. That's what we call an equilibrium, because your y prime is basically 0. You never change. Your next time is going to be the same as the current time. Sounds good? Great. We're going to talk more about this one later, but now you can see a very interesting fact. Can your population ever grow like that? The answer is no. Why? Because this is one solution, which is my equilibrium, and my solution never intersects, remember? Due to uniqueness. Therefore, you will never go like, yeah, your capacity is 5,000. Is that possible that I first grow to 5,200 and then I drop back to 5,000? The answer is no. You actually always go from below. You never come up. That's the beauty of uniqueness. So I'm going to write it down. Uniqueness guarantees the solution never cross the equilibrium solution. That means once you have a DVQ, you can use the equilibrium to divide the DVQ, the solution, into several regions. What happens in the region stay in the region. Good so far? That means if you solve this DVQ, what's going to happen? Well, it depends on your initial condition, but it's either this or this. If you want to include negative, you can have something like this. You will be able to classify what solution you will get. You will know how many different types. And they are separated by the equilibrium. And all of this, thanks to the uniqueness, they never cross the boundary. Sounds good? Okay, later we will talk about how to define your equilibriums in different types. For example, for this one, you can see if you're from 1, you're above 1, you're going to be actually go back to 1. If you're below 1, you're going to grow back to 1. This one is something we call a attractor or a sink. This is where you stay, not changed. But if you're a little bit away from it, you got attracted back. Sounds good? Now look at this one. What's going to happen? If you're 0, you stay 0. If you're a little bit positive, you will actually go away from 0. If you're a little bit below, you're going to go away from 0. Make sense so far? This is the second type of equilibrium. That is called a source. Application is trivial. Let's say you have 2 planets. They are in equilibrium. They don't move, or they move in a very stable pattern. Good so far? Now what's going to happen is I'm going to go inside, I throw a nuclear weapons on one planet to move it a little bit, to disturb it a little bit. Still okay? What's going to happen next? Well, it depends. If the original equilibrium was stable, which means a sink, you disturb it a little bit, it comes back and got attracted back again. If the original equilibrium was a source, it's not stable, you disturb it a little bit, that thing just go far, far away and keep getting away. That's how we define a stable and not stable equilibrium. Because it's all here, it's deeper than what we just see here. Sounds good? Finally, back to the example we had before. Remember, we try to solve y prime equals et sine y. What we had before was we did an Euler's method. Nothing tells us it looks like this, and then suddenly things like that. It's really bad. Our question was, is it because the original function is bad? Or is it because the numerical method gave me something ridiculous? Computer just went crazy. Or maybe my method is bad designed. Now think about what's going to happen. Well, number one, let's talk about the equilibrium solution. That happens when sin y equals 0. That happens when y equals n pi. Right? So I can draw all these equilibrium solutions there. It's actually 0, pi, 2 pi, 3 pi, and so on. And every single one here is an equilibrium solution. Okay? Now, can your solution look like that? No, it crossed my equilibrium. It can't happen. Therefore, something is wrong with my numerical method. Can't happen. Therefore, something's wrong. The numerical method need to be investigated. Thanks to uniqueness. All right. Any questions so far? This section is basically over. Existence and uniqueness. Yeah, Doug, what was your question? I kind of thought you just lower your hand after a while.
Can you hear me okay?
Yep.
Sorry, my mic's been weird. So with the uniqueness theorem, with the idea that, could you scroll back up to the one where it's the graph kind of reaching the equilibrium? Yeah, that one right there. So in looking at that, since the graphs can't intersect, could we have a series of graphs that I'm picturing like a bunch of them kind of overlapping on top of each other? Like,
hold on. Let me write it down. For the same exact differential equation with the same exactly dpq. Now you change your initial value, you got something like this. Now you change it again, you got something like this.
Yeah.
Okay, what's your question then?
Just with that idea, so we can draw that series of graphs and they're never going to intersect because we know they're unique, like no matter the number of graphs, because we have uniqueness.
If they intersect, they violate the uniqueness. That's why they never intersect. So that's great. Mm-hmm. Yeah. Another thing you can think about is like if you have a solution going like that, if you have a solution going like that. Now I ask you to predict, if I know the data now is like, I don't know, 20, 2000, how do you predict what's going to happen next? Well, which one are you going to follow? Mm-hmm. Right? So that's why I say, hey, you're basically saying the future is not deterministic. You're saying, hey, with the same starting condition, I may have a solution 1 or solution 2 or solution 3. Half the time, 1/3 of the time. That's not how we do physics, right? Mm-hmm. Then you can see why this one fails for quantum mechanics. Because in quantum mechanics, that doesn't go with probability. Calculus is not the right way of doing it. Cool. All right. So that's what we have for existence and uniqueness. We talk about something very important that is called equilibrium. So let's talk about equilibriums. Equilibria and phase lines. In this section, we only talk about autonomous ODE, which means your FTY only depends on Y. There's no T. All right. The first thing we want to do is we want to introduce a concept which is called a phase line. Let's take example. Y prime equals Y times 1 minus Y. phase line is a line with respect to y. So this is your phase line. Now I am going to do several steps. The first step is try to find where y prime equal to 0. In this case, y equals 1 or y equals 0. Now you know we're looking for equilibriums. Here's 0, here's 1. The second thing we want to find out is, since this one is 0 here, this one is 0 here at 1 and 0, this one naturally divides this one into 3 parts. Bigger than 1, 0 less than y less than 1, and y less than 0. Okay. Then on each part, I can determine if y prime is positive or negative. They're exactly 0 at the points, then not at the points, they're either positive or negative. Good so far? So let me write it down. For number 2, we have 3 parts. Y less than 0, 0 less than y less than 1, and y bigger than 1. You can plug in some test numbers, or you just go with simple quadratic algebra. The shape is a parabola. You can easily see this is y prime less than 0, y prime bigger than 0, and y prime less than 0. Okay? Now with this information, the third thing is we're going to draw this information on this line. The rule is, if y prime is less than 0, you draw an arrow, which is going down. Make sure it's actually for the bigger than 1 part. Bigger than 0 if it's going up, and less than 0 if it's going down. This whole thing here is your phase line. Sounds good? Okay, quick notes. Find where the thing are 0, then you have several parts. For each part, determine if it's bigger than 0 or less than 0, just draw the corresponding arrow. Okay, it's not possible that for one area you have either an up or down. That means your y prime can be sometimes positive, sometimes negative. That means your y prime is 0 somewhere. You missed equilibrium. Good so far? Your y prime change continuously. How can it be positive and negative in the same interval? It cannot be. Unless it crosses something, then you're missing an equilibrium. Put it there. So for each interval, you only have one sign, either bigger or less than. Okay? Of course, this is easy. Why is it important though? Let's talk about using phase line to sketch the solution. This is, of course, roughly. You cannot be accurate. Okay. Let's go back to this one. And we already know the phase line look like this. Okay. Remember, before we know the solution looked like that, because we actually solved it. We actually don't know the solution looks like this just by looking at this differential equation. Okay, but now we will be able to draw it roughly according to this phase line here. And this is how we do it. Number 1, you take the equilibrium, you just extend it to be a horizontal line. And this is definitely your solution. Okay. Second, You start with some initial value, anywhere of your y, for example. You go to the right. This arrow here tells you y prime bigger than 0. That means when you go to the right, you draw this thing as an increasing function. Number 3, the principle is do not cross the equilibrium. This will force you to look like this. Okay? Again, pick an initial value. In between, you have to increase, but eventually you cannot hit that thing. So roughly the sketch is the solution look like this. Can you draw the other two part? The part above 1, you start from here. Your phase line tells you you should go down, but you could never cross equilibrium. Therefore, your solution look like that. Okay, you start from here. Your phase line tells you you should go down. This time there is no equilibrium. Therefore, you should go forever. Sounds good? In this way, we can draw the graph, rough graph, okay? Technically, I only know this one goes up. I don't know if it's like this or that or whatever. I don't know. But roughly, the sketch looks like this. And in this way, we don't have to solve anything, right? We didn't know the solution looked like a S-curve. We didn't know that. We just used the simple phase line, and we did it. Sounds good? Similarly, let's try some example yourself. Let's try the one, remember the free dive, the skydive. We have mv prime. Okay, let me make sure I get the right one. Mv prime, I deleted it, either way, equals mg minus a k v square. That's what we had last time. Okay, for the free diving, we try to solve it. Now ignore the m and the g and the k, they're just constant. Let's try either one, which is, let's use y. Y prime equals 1 minus v square, which is roughly the same shape as this with a different constant. Okay. Go ahead, try to draw the phase line for this. After you draw the phase line, try to finish the solution. Try it yourself. Sounds good. So again, we didn't solve it, but we somehow know roughly what the solution looks like. Okay? And it matches common sense. You start with some velocity. Eventually, you're going to receive the final velocity, which is you're dropping at a constant speed. Okay, that is because the whole thing, your error resistance equals your gravity. Okay. Another interesting thing here is like if you don't do free dive, you actually take a airplane. Okay, an airplane has something to shoot you down, which give you a very, very big initial velocity. You're actually going to first slow down, which is really interesting according to this solution. It's just like, hey, you're going down, but actually you're going back. Of course, you will be dead because the force is too strong. You cannot hold that as a human being. Okay, but first you don't actually accelerate, you slow down. Okay, and then until this, you reach the equilibrium. That actually happens to some freediving. Have you guys seen that? It's just like the moment you open your parachute, you actually go up a little bit. It's not like you slow down a little bit, you actually go up. Okay, that's actually real. That is also guaranteed by this solution. Okay. We don't do many more examples. I think you get the idea. For example, I can give you something. This is something you definitely don't know how to solve. But now, given what we just did, it's very easy to actually draw the equilibriums and find, okay, -5, 2, -3. On each part I'm positive, negative. I know how the solution is going to look like. Okay, that's the beauty of doing things in phase line. Not accurate, but good enough. So I will skip that. Okay. Some nice thing to think about. The first one is your solution may not exist all the time. And we can try this one. Okay. Try to draw the phase line. It's pretty simple. It's just -1. Before -1, going up. After -1, going up. Okay. Then if you think about a solution look like this one should go up forever. For sure. But now if you solve it, which is separable, by the way, we can solve it. This is the solution. Now if you take a look, this will become interesting. Okay. Maybe put it the other way. You draw it, the graph look like this. Okay, keep in mind your phase line look like this. Okay, so according to your phase line, this one keeps increasing. The answer is yes, this one actually keeps increasing, but this one actually does not hold towards infinity. Good so far. If I give you something, you may think the graph should look like this instead. You may think the graph should be something like, if it's like that, then go this. Oh, let me draw it. You may think the graph look like this. Going up, going up. Therefore, if you start from here, you go like that. And if you start from here, you go like that. Sounds good? But the real graph is actually not what you thought. It's not as simple as this one. You actually have both parts at the same time. Meanwhile, this one does not go to infinity. This one goes up to infinity at finite time because you have a vertical asymptote. So phase line is correct, but can't tell if the solution blow up, which means goes to infinity. Infinite time. Phase line can't tell you that. Okay. Second thing I want to talk about is y prime equals 1 over 1 minus y. Phase line. Number one, y prime never equals 0. There's no equilibrium. There's none. Second, this one does have a positive or negative. It happens at y equals 1. Okay? When y is less than 1, this is positive. When y is bigger than 1, this is negative. Still okay here? So let's draw the phase line. How are you supposed to draw a phase line? Well, number one, this phase line does have two parts, this and that. Second, this one does not have equilibrium at 1. This one does have something which does not exist at 1. So make it natural to put a hole here instead of a 0. This is 1. This time, technically, I write it down, but keep in mind, there is no solution here. It's just a line, not an equilibrium. So this one is empty. I just write it down to as a mark. Sounds good? Now, according to our old experiences, we should draw something like that. We should draw something like that if it is an equilibrium. And the reason is because this one cannot cross this. That's why you have to go that way, right? But keep in mind, this time there's no equilibrium here. It's a circle. You can check by yourself. You can solve it yourself. The solution actually looks like this. Sounds good? Okay, so the phase line still work. It's still correct information. Just to keep in mind, don't get too excited. You just say, hey, this goes here, this goes here. Well, before, that was because here's an equilibrium. This time, you don't. You don't have something flat. That's not a solution. Therefore, there's no guarantee they don't intersect. They can intersect with a hole there. Okay, but if this is not a hole, it's a dot, definitely a horizontal asymptote. All right. Is everything clear for this part? Phase line. I would say most of the time for the exams and in real life, you should have something as reasonable as this because usually the function is nice. Okay? If the function is weird from the beginning, it may not even exist if it fails to be continuous. Okay? It may not be unique if the partial derivative fails to be continuous. So in real life, most of the time, you will be handling things like this. Okay, but just keep in mind, things can go wrong. All right, number 3, let's talk about equilibriums. Again, that happens when you have Fy equals 0, which is technically y prime. Zero derivative means no change. That means the solution stay on. Okay. Number 1, why do you care in real life? Well, I'm just going to write down several names. Population equilibrium. Thermal equilibrium. Okay, potential equilibrium, energy equilibrium, whatever. Okay, have you guys heard about those kind of terminology before, especially the second one? Thermal equilibrium. Okay, so that's the first hint. The solution itself is interesting enough. Itself is interesting. Already interesting. Not to mention the additional functionality. It can divide the whole thing into different regions and tell you what other solutions are. Even itself is interesting enough. Okay. Then let's talk about what information can you get from the equilibriums. Let's call it classification of equilibriums. We had it before. Okay. Y prime equals y, 1 minus y. We have 2 types of equilibriums here. The first type is the solution stay here, but if you're a little bit away from the solution, you come back to the solution. We call this a sink. Some people call it a attractor. It is also related to the word stable. You are a little off, you come back. To picture that, just think about a sink. Okay? If you pull water right into the hole, what's going to happen? The water ends up in the hole. Now, if you just go a little bit away from the hole, what's going to happen? Well, that thing rotates and eventually still go into the hole. Okay, that's why it's called a sink. If you're a little bit away, you still come back. Now, the second part is something like this. Wrong direction. This direction. You can see, if you are a little bit away from 0, if you're above, you keep getting away from 0. And if you're below, you keep getting below. That means once you leave the equilibrium, you never come back. You become further and further. Still okay? So this one we call a source. A source. It's related to unstable. Some people will call it a diffuser. Okay. An easy example to see is this time you just take the sink and make it bottom up, something like that. You start to pour water here. If you're really good, nothing just right hit the small hole here, the water still stay there, right? But as long as you're a little bit off, this one just goes away and never come back. Still okay here? That's what we mean a source. Now, for example, a very simple example, think about the potential energy. If your potential energy looks like this, right? This is your lowest potential energy. If you start from here, you stay there, you never move. Good so far? What if I give you a bump? I just say, hey, your initial energy, I give you initial energy to make you here. What's going to happen? This is going to be attracted back to this. Still okay? Okay, and then you have a little bit momentum and then come back. So you start to shake like that. So harmonic oscillator is actually a sink. You shake that thing, it's not going to break the spring. It's going to come back and eventually stay at the lowest energy. Sounds good? Okay. Second, what kind of potential energy is not stable? Something like that. If you're here, you're stable. As long as you're a little bit off, what's going to happen? You never come back. You always go with the lowest energy, right? Black hole look like this. Okay, so that's how you actually use this one later. But for now, it's roughly something you can think about. Sounds good? Cool. Now we have a sink. Now we have a source. Okay. The question becomes, how can we quickly tell if something is a sink and something is a source? Okay. Well, number one, I know where they are. It happens at Fy equals 0. That's where they are. But still possible, they can be this or that. Then number two, how can I tell if it's this or that? It really depends on if I have this one, I draw this. This is going to be a sink. This is going to be a source. Okay, so what happened here? As y increase, which means we go from bottom to up. Okay, y prime equals Fy went from positive to negative. Okay, these two facts combined together tells you F prime y is less than 0. As y increase, your y prime, which is Fy, went from negative to positive. Okay, negative to positive as you go up. This implies your F prime y is bigger than 0. Okay, read it. Does the logic make sense? Saying this is basically saying the arrow has to be in this format. Okay, so basically as your y increase, going from bottom to the top, originally you were increasing, which means you're positive. After a while, after this point, you become negative. That's what happens in this picture, right? Okay, that means as your y increase, your fy actually decreased. That's why f prime y is 0, less than 0 from here. Okay, similarly, this one is bigger than 0 from there. Then we have the linearization problem. Let me see. Linearization theorem. Okay, suppose we already know y0 is an equilibrium. Okay. Then y0 is a sink if y prime, which is fy, oh, it's not y prime, fy prime is less than 0. Y0 is a source if this one is bigger than 0. Number 3, this one is called a node if this one equals 0. So we have a quick way to check if something is a sink or if something is a source. Okay. Moreover, just a side note for node, what can happen? Well, if this is your f prime y, it's 0 right here. This can happen, which means both are positive. Your phase line is going to look like this. For your f prime looking like this. Both positive before and after. Or your phase line can look like this. Then they're not a sink or they're not a source. But it's also possible that your thing look like this. Right? So it's still possible this one is a sink or a source. You just don't know unless you go further. Sounds good? So for node, it doesn't mean that it's not a sink or source. It just means all the three are possible. It can be your sink, it can be your source, it can be neither. So don't just say, hey, if it's a node, it's not a sink, it's not a source, it's wrong. It's still possible. Okay, so additional information is needed. All right, that's all for today. Feel free to leave and